So the length of the triple bond is lower when we are comparing the single bond one. In terms of strength, again also, the triple bond is stronger than the double bond and the single bond. In terms of IR frequency, again also, the higher the strength, okay, the higher the strength of the double bond, the higher the frequency. And again also the single, when we are comparing in terms of single bond, there is the lower frequency. So there is the decrement of the decrement of the frequency when we are moving from triple bond, double bond, and single bond respectively. So when we are comparing these values, carbon triple bond carbon, carbon double bond carbon, and carbon single bond carbon. So there is the decrement of frequency when we are comparing the strengths of the bonds. So K is a constant that varies from one bond to the another, one bond to the other. As a first approximation, the force constant for a triple bond are 3 times those of a single bonds, whereas the force constant for double bond are twice those of a single bonds, bonds. So there is two things should be noticeable immediately. The one is, the stronger the bond have, the larger the force constants, okay? The larger the force constant, okay? And vibrates at high frequencies than the weaker bonds. And the other one is the bond between the atom of the higher masses, large reduced mass, vibrates at low frequencies than the bonds between the higher atoms. So this is the CH stretching occur at about 3000 centimeter universe. So this is in terms of the mass. In this case, the mass is the hydrogen is the one. In this case, the carbon, the oxygen, chlorine, bromine, and iodine. So the carbon is constant, and the attached atom, the mass of the attached atoms are this varies. So when we are looking this one, okay, at the atom bonded to the carbon increases in the mass, the reduced mass again also increase, and the lower frequency of the vibration there. Okay. So just let me repeat this one. At the atom bonded to the carbon increases in the mass, so the reduced mass increases, and the lower the frequency of the vibration, lower frequency of the vibration. In terms of hybridization, so the sp greater than the sp2 and greater than to the sp3 in terms of bonds, okay, in terms of the strength. In terms of resonance, so when the conjugations lower the energy to the vibrate the bond. Okay. In this case, here you have alpha beta, the conjugation. In this case, it is isolated ketone, so there is no conjugation. So here you have alpha beta unsaturated ketones. In this case, again, also there is a conjugation. And when you come to alpha, beta, gamma, so here you have again also other conjugation. So the conjugation is lowering the energy to vibrate the bond, Here you have for simply the ketone 1715. And when we come to for alpha, beta, or if there is the conjugation double bond 1690. When you come to this one, 1675. So there is the decrement of the frequency. So in terms of resonance, there is the conjugations are lowering the energy to vibrate the bonds. So this is the absorption regions. The absorption regions. So this is the plot of the IR spectrum. The plot of or the output of the IR spectrum. It exists between 4,000 up to 400 centimeter inverse. So the x-axis is the wave numbers, and this one is the percent transmittance. So around these regions, these regions, there is the OH, the NH, and the CH stretching spectra. If there is the OH functional group or the NH or simply the CH stretching, so it produces a spectra under this region. If our pharmaceutical active ingredients have carbon triple bond carbon, carbon triple bond nitrogen, so it produces a spectra around these regions. If our compounds produce a spectra under these regions, maybe that compound is carbon-carbon double bond, carbon double bond oxygen, carbon double bond nitrogen. So this is the stretching one. So this one is the fingerprint region. So this is in this region there is the stretching and the bending, or the combination of the bonds that exist. So for the beginner, so just have to be ignore this part. So simply focus your interpretation between 4,000 up to 1,400 centimeter inverse. So this is a simple complex regions. So the normal mode of vibrations. So as we have discussed before, when the vibrations may be stretched or compressed by zinc, when we are let's say when the lights interact with our samples, maybe our samples is stretched or compressed, just like the spring. This is a simple mode of the vibrations. So vibrational types, or simply types of vibrations. There are two modes. The one is the stretching, and the second one is the bending. When we say it's stretching, it affect the bond length. The bond length. When we are talking about the bending, so it affects the bond angle. So let's say just have to assume this one. It is by molecules. So this is the one atom, and this one is the atom. So this is the bond. So this is, assume this one is the other molecules. So when the IR interact with our sample, okay, our samples, so there is the stretching of the bond, maybe symmetrical or simply asymmetrical. When the IR again interact with our pharmaceutical active ingredients, maybe the bond is bending just like this one, Okay. In the bending, there are different types of bending. There is scissoring, twisting, rocking, wagging. We will discuss this one. But generally, we have two types: the stretching and the bending. Stretching and the bending. So this is the bending vibrations. The bending vibrations are subdivided into four: the scissoring, okay, scissoring, rocking in this way, and this one is the wagging. So this is the out of plane. The two is move just like this one, out of plane. In case of scissoring, it's look like this one. Okay. In case of rocking, just like this one. Okay. In case of wagging, just like this one. Very well. The two bonds move the out of plane. In case of twisting, again, so it's out of plane. It's move turn by turn. Here you are, just like this one. Okay. So generally, in the bending vibration, they are subdivided into scissoring, rocking, wagging, and twisting. So this is again also a simple vibrational modes. See the stretching, the two bonds. Okay, the two bonds equally stretched is known as symmetrical stretching. When we come to this one, the one is this is the different directions. Here it is a different direction. So say types of stretching is known as asymmetrical stretching. When we come to bending, so as we have discussed before, so this one is the scissoring. It exists around these frequencies, and also another one is the rocking. So this rocking is exists around say types of frequency, and the other part is the wagging. Again, also here it was say types of vibration. So again, so this say types of frequency. The fourth one is the twisting one. So here are the simple animations for types of vibration, or simply for vibrational modes. Here it is. This is the stretching vibration of the atoms. Okay. Here it is. This one is the asymmetrical one. Okay. Here it is. This is the movement of the stretching of the bond. Here it is equally stretched. Okay. Equally. So this one is going about symmetrical stretching. Symmetrical stretching. When we come to, so this stretching exists around these frequencies. This frequency. When we come to the bending vibrations, scissoring, like this one. Okay. When the IR light interact with our samples, the bonds vibrate just like this one. So again, also when the IR lights interact around this frequency, which means almost 1400 frequencies, so it's twisting. Twisting is looking like this one. And this one is wagging around this frequency. So this is rocking around 1150 frequency. So this is a simple vibration modes for stretching and bending vibrations. This one is the same with the previous slides. The other one is the molecular vibrations. The molecular vibrations. So how many vibrations are possible? Or simply, how many fundamental vibrations are there in the molecular vibrations? So the molecule has as many degrees of freedom as a total degree of freedom of its individual atoms. Each atoms has 3 degrees of freedom, particularly the corresponding to the Cartesian coordinate XYZ direction. Thus, in an n atom of a molecules, there will be 3n degree of freedom. N atom of the molecule, there is 3n degree of freedom. That is the Cartesian coordinate. Okay. So there is in this vibration mode, there is a translation and the rotational of the vibrations. In case of translation, there is the degree of 3 degrees of translational freedom is there. Okay, 3 degrees of translational freedom is there. In x-axis, there is translation. In the x-axis, the y-axis, and in the z-axis. So it's possible to translate the atom. In the rotational, in case of rotational, so the interatomic distance remain constant. but the entire molecules rotates with respect to three mutual perpendicular axes. So the three rotational freedom for nonlinear molecules, and again also for linear one, there is two rotational freedom. Okay. In case of linear molecules, there is the backward and the forward direction possible to rotate in the two directions. In case of nonlinear molecules, there is three rotational freedom x, y, and the z-axis. So fundamental vibrations. So here it was is the degree of freedom of the translational, rotational, and vibration. In case of translational, for linear molecule, there is 3. For non-linear one, here it was 3. In case of rotation, okay, for linear and for linear molecules, there is a 2. And for non-linear one, for 3 in x, y, and z direction. So generally for vibration, 3n, which means n is a number of atoms. Okay. 3 times this 3 stands for the x, y, and the z direction. So totally the vibration is 3n minus 5. 5 stands for the summation of translational and the rotational one. So this is for vibrational mode for linear molecules. And this one is 3n minus 6. 6 stands for a summation of translational and rotationals. So this one is for nonlinear molecules. So if you want to calculate the vibrational freedom or for a number of vibrations for linear molecules, so this will have to be these formulas. And if you have nonlinear molecules, so this will have to be applied this formula. This is a simple examples. So determine the number of degree of vibration or vibrational freedom for each of the following molecules. If you are hydrogen cyanides, so in this case the molecules is a linear. So okay, the molecules is a linear. In this case, this molecules again, so it is non-linear one. If the molecules is a linear, so this have to be applied 3n minus 1, 3n minus 5 for linear molecules. So this n stands for the number of atoms. So to calculate here, it was 3 times number of atoms is 3, so 3 times 3 minus 5. So we have 4 number of vibrational freedom. Now let's come to the classification of IR bands. So IR bands classified as strong, medium, and weak. So this is depend on the relative intensity of the infrared spectrum. So strong bonds cover most of the y-axis. Okay. The y-axis, so here it is the strong bonds cover most of the y-axis, and the medium bonds falls to about half of the y-axis, cover half of the y-axis, and the weak bonds falls to about 1/3 or less of the y-axis. So it's covered the weak one, So this is the strong. So it's covered about the all parts. This one the half, and this one is the 1/3 part. So this is a classification of the IR bands. Bonds. Now let's come to infrared active bonds. So not all covalent bonds display the band in the IR spectrum. Only polar bonds do so. So it's known as IR active. When you say it is IR active, it's only a polar bonds exist between the bonds. So here you have there is the classification of the IR active bonds. So this one is the strong polar bond, such as carbonyl groups. So it produces strong bonds. It produces the strong bonds. When we come to this one, okay, when we come to this one, so it is a medium polarity bonds, and it's asymmetrical again also. So it produces a medium bonds, and is also a medium polarity bonds exist between the two atoms. So this one is the weaker, okay, the weaker polar bonds, and the asymmetrical and asymmetrical bonds produce weak or not observable bonds. So in this case, there is the weak polar bonds exist between the atoms. So it produces a weak bonds. In this case, there is asymmetrical, there is a symmetrical bonds. In this case, this one is the same. This one the same with this carbon bond. In this case, here you have carbon. In this case, again, also here you have carbon. So it's the same. So this one has symmetrical bonds. So in this case, it's not observable, or it's not produce IR spectrum. Not produce IR spectrum. Now it comes to the infrared band shapes. Okay, so infrared band shapes come in various forms. So generally we have two most common bands. The one is the narrow, and the other one is the broader one. So this one is the broad band. So say types of spectra are produced especially when the OH functional group exists in pharmaceutical active ingredients, or in the carboxylic acid, because in carboxylic acid there is COH or OH functional groups again also there. So it produces the broad band like this one. The other one is the narrow band, so it will be like this one. So say types of band is known as it's a narrow band produced for carbon double bond oxygen, and in case of carbon double bond, it exists around this frequency. So this is the narrow, and the broad bands are there. The other part is the fingerprint regions. Although in the entire IR spectrums can be used as a fingerprint for purpose of comparing molecules. So around 600 up to 1,400 centimeter universe range. So this range is known as fingerprint region. So it's a complex and it's difficult to interpret for a beginner. So just you have to be focused your interpretation around these regions. So this region is known as the fingerprints. The fingerprint regions. It's a complex area and overlapping each other. So it's difficult to interpret for a beginner. So your analysis or your interpretation of a spectra simply focused on around these regions between 4,000 up to 1,400 centimeter inverse. So now let's stop in here. We will continue part 2 in the next time. Thank you for watching.